Hi, welcome back to our machine learning course. Now, one of the most fundamental insights in machine learning is that if you take a large model and you pre-train it on lots of data, those models tend to learn very fundamental things of the world. And we can reuse those learnings to solve new problems, which we call transfer learning. So we can just load the model with the learned weights and then fine tune them, use them as a starting point, and then fine tune them to the new task you want to learn. Right? So we can take a large model like ResNet pre-trained on ImageNet, and then fine tune them to recognize dogs and cats. And hopefully that will give us a better starting point than starting the network from scratch. So the way we do that is by taking all the convolutional layers typically. This looks like a VGG network, right? So we take the convolutional layers uh, with their original weights, and we can either just keep all of them frozen and then add more dense layers and a classification layer head at the end. And then we can, for instance, freeze those and then learn only the last part, the dense layers. Or we can say, well, we'll keep most of them frozen, but we will make the last block of convolutional layers trainable, for instance. Or we can say, well, we'll just use them as an initialization, and then as a starting point, but I will still update all of those weights to learn my new class, my new task. Right. There are different ways that we can actually do that, and we will see that different ways are better for different applications. Side note, we typically don't want to keep the original um, classification head or the original fully connected layers because those were trained on ImageNet on like 1,000 class problem. If your target problem has 2 classes, then well, it doesn't make sense to keep those convolutional layers, and especially not if the classes you want to learn are very different from ImageNet, then it doesn't make sense to keep those convolution layers because those convolution layers were trained particularly to map the embedding to a particular output class. But the embeddings themselves might be useful. We just need to then learn a new mapping between the embeddings that come out of this convolutional part um, and the class that we want to predict in your new task. Okay, like I said, there are different ways that we can do that. The first easiest one is fast feature extraction, which means that we keep all the layers, we keep them frozen, we add a few layers at the end, maybe just like one hidden layer and an output layer, and then we just learn the last part. Right? You don't even have to use layers at the end. You could just take the embeddings and then give them to a random forest, right? That's also possible. Although mostly people will just add dense layers at the end, like a linear model at the end, to then map the embedding to the final class you want to do. This typically only works, well, this is typically most useful when you have a small target task, right? So say your new task only has a very limited number of examples, and it's also very similar to ImageNet or whatever data set this model was pre-trained on. Right? If it's very different, then well, it's probably not that useful, probably. But yeah, it's that those cases. So it's similar problem, and your target task is small. Then this is probably the best thing to do. Now, if you have a little bit more data, then you may actually want to pre-train those. You can keep those. You can start with those pre-trained weights, but you can fine-tune those weights as well, right? So this requires that you have a lot of data. Otherwise, you won't have enough data to update all these weights. But if you have a lot of data, then that's useful. This is also called end-to-end fine-tuning. We'll still add a new classification at the end, of course, for a new class. and we'll train this one, but we'll also fine tune those convolutional weights as well, hoping that we can still tune the filters just enough that they will become particularly good at distinguishing the classes from our new task. Um, if you have a situation where you have enough data, but the new task is very different from what you had before, then it may actually be better to keep the first layers frozen, because those guys, they learn mostly the patterns which are useful in general, like the horizontal lines and the colors and the simple shapes. Right? But you unfreeze the last part of the convolutional layer, because these layers, they learn to distinguish the different classes we had in ImageNet, right? If your new problem is very different from that, say it's microscopy data or astronomy data, it's super different, then you may not do anything with those last layers, right? Because they're learning how to distinguish cats and dogs and cars and trees and so on, right? So you want to basically entirely fine tune those to the new class, the new kind of objects you try to learn, right? Yeah, we also call this partial fine tuning. So we freeze the first part, and then we unfreeze only the last parts, and we're gonna fine tune them to our new task. Right? We have always option 4, which is yeah, we just train from scratch, but that's not transfer learning. If your new task is, if you have a lot of data and you have and your task is very different from anything you've seen before, then it's typically better to just start from scratch. Okay, this is how we implement those things in PyTorch. So in each of these, we'll start by importing ResNet 18 or any other model that you want. And we're going to include the weights of ImageNet, pre-trained weights. And in the first case, feature extraction, we are going to replace the head. So in this case, this is a ResNet. In ResNet, the features are the convolution layers, and FC, fully connected, that's the classification head. We're going to replace the fully connected layers by an identity layer. This is identical to just removing the old head. But we do it this way because it's just implementation makes it easier. And then we're going to create a new classifier, which is just a linear layer, which is going to map whatever comes out of the convolutional part, the number of outputs of the convolutional part, and map it to one new class that I want to predict. Well, it's two classes, but one head that I want to predict. Yeah, and then I'm going to say all my parameters in my backbone, it's not specified here, but that's the convolutional part of the ResNet. Gradients are false, so I'm going to freeze them, not going to fine tune them. And I'm going to feed forward, I'm going to feed new information, new images to our ResNet. The outputs are my features, and I'm going to give those features to my classifier, get the logits, and then return those, and then I can train this model, right? And training means only learning the last linear layer. Right. If I do that, I see that I immediately get a big jump. If you remember previously when we were learning from scratch, we were happy with our model in the end, that it can kind of learn nicely, right? This one here. So we get up to, yeah, maybe 85%. We could maybe get a little bit more by training longer, but this is probably the best we can get, is around 85%. By doing simple transfer learning, even in a few epochs, we get up to 90%, and you improve a little bit up to maybe 93, 94% accuracy, validation accuracy. Right. Such a huge improvement from 85 to 94, right? Um, but we also see that it flattens out beyond that, right? Because all we're doing here is training my linear layer, right? All the other parameters are frozen, right? We have actually only 512 trainable parameters, all the rest were frozen. And so there's no capacity anymore to learn anything else. Okay, we can try to see whether unfreezing the last blocks helps. So in this case, we're gonna first freeze all the layers, and then we're gonna unfreeze um, the layer 4 parameters. This is the last convolutional part of the ResNet. It's a lot of ways by the way. This is a pretty large block in the ResNet architecture, but we're gonna set them all to requires GRUD, so they're trainable, they're unfrozen. If you do that, we end up with 8.4 million trainable parameters, and we see the performance is, yeah, maybe slightly better. It gets slightly closer to 95%. So that's a little bit of improvement, but not that much. And also, again, after some epochs, we kind of flatten out. There's no further learning happening. Right? So it seems that the weights, they're pretty set in their ways, and we're not very successful in like bringing them to very different values. So they're already converged, and they won't change that much anymore. So yeah, in this case, the fine tuning is not that super impactful. It could be very likely because the cat data set is very similar to ImageNet. ImageNet has a lot of cat and dog images, has multiple classes for many types of cats and dogs. So it's very good already at classifying cats and dogs. So that's why probably fine tuning doesn't really help that much, because ImageNet is already fine tuned on cats and dogs. Finally, what we can do is end-to-end fine tuning, and this simply means that we're going to take all the parameters and we're going to make them all require GRUD, right? So they're all going to be trainable. If you do that, by the way, make the learning rate small, and actually make the learning rates of the convolutional part small, right? So we're going to set two different learning rates. We're going to set the learning rate of the ResNet parameters very, very small, 10 times smaller than the ones in the final fully connected layer. If we do that, then we put the focus on tuning the weights of our dense layers at the end, and we are going to very, very carefully tune the weights of our convolutional part. And if you do that, well, yeah, it's not much better. It's not surprising because we were already tuning 8.4 million parameters here. Now we're training 11, but few more. And we're training the very early parts of our convolutional layer, which were, again, probably already pretty stable. So in this case, for cats and dogs data sets, it's not making that much of a difference, but it may make a difference for your new task. All right, that's it for the lecture on convolutional layers. So we learned that convolutional layers are ideal for addressing image-related problems. They're much better than anything else that we've seen so far. By the way, we can also use 1D ConvNets for things like text or signals, although in the next lecture we'll see better ways of dealing with text. We learned that compositionality is very important, and by adding many convolutional layers after another, and the deeper the better really, we can learn hierarchies of very simple patterns up to very complex patterns that can represent anything in the real world. And that's a very important aspect of learning as well. We learned how to achieve translation invariance by building deep networks, hopefully with some large enough filters and max pooling in the mix, so that these models are robust to changes in the input image. If the input image would shift left or right, it wouldn't affect the output at all. That's translation invariance. We've seen how we can use data augmentation to create more data to help fight overfitting. We've learned how to inspect the model, how to visualize activations, the filters, and GradCam, looking at what the model is looking at when it makes predictions. And we've seen transfer learning, how we can reuse pre-trained weights to learn new tasks faster with much less epochs and much less data. Okay, thank you. That's all for this very long lecture. I'm looking forward to the next one.